Hello, today we're going to be taking some notes on section 5.4. Our lesson begins on page 7 of your chapter 5 notes packet. We have so far learned in this chapter regular plain old-fashioned probability distributions. They were the tables in sections 5.1 and 5.2. And then in section 5.3 we learned the binomial distribution. So now in section 5.4 we're going to be talking about the multinomial distribution. Okay, we have a couple more. So our objective, we're going to be talking about the multinomial distribution, the Poisson distribution, and the hypergeometric. This looks like fish. It's fish in French. Poisson, it looks like poison. It's Poisson. We'll get there next page. So multinomial distribution. We just spent time on section 5.3 talking about the binomial distribution when there's only exactly two outcomes, success and failure. Now, multinomial is when there are more than two outcomes in each trial. All right, so if you have to choose out of 5 places to vacation in, there are 3 possible responses to a survey. Anytime you have multiple categories, more than 2, then you can use the multinomial distribution. Here's your formula. That again is probably one of those that you're like, oh my goodness, and it's really, really not that bad. So I'm actually going to describe it after we set up the first example, and then I'll show you how to put them together. So in a large city, we have the categories of 50% of people choose a movie, 30% of people choose a play, and 20% choose shopping as a leisure activity. So right away, I'm going to start organizing my work. I've got movie, I have the play, and I have shopping as my 3 categories. And 50% of people choose the movie, 30% of people choose the play, and 20% of people choose to shop. Okay, now we have, if a sample of 5 people is randomly selected, we want to find the probability that 3 are going to go to the movie, 1 goes to the play, and 1 goes shopping. Your X's need to double check that they add up to our total sample size of 5. Now, this portion is not required of you. You're allowed to just jump straight into the formula. But I have found that by organizing my work, it is easier for me to then put it into the formula. The probability of that happening is we have n factorial, okay, 5 factorial, over, you're going to do each of your x's factorial in the bottom. So we're going to have 3 factorial, 1 factorial, 1 factorial. All right. Then you multiply it with its each probability raised to its x power. So you're going to have as many of these as you have categories. So I'm going to take the P for probability, the probability for movie, 0.5, and raise it to its x, 3, times 0.3 raised to its x, 1, times 0.2 raised to its x, 1. All right, now, of course, you don't have to actually raise it to the 1 power in the calculator. Raising to the 1 power leaves it the same. Just like 1 factorial is 1, dividing by 1 leaves it the same. But it is important that you write it all out so you make sure you got it all. Your exponents need to add up to your n. Okay? Then, when you type it in, you're going to type it in one shot. Okay? So you're going to type it in. You're going to create a fraction by doing control divide. And you're going to have 5 factorial over 3 factorial. I'm not going to put the 1 factorials in the denominator because it's just dividing by 1, but you can. I'm going to go to the right. I'm going to have my parentheses. I'm going to have 0.5 to the 3 times 0.3. You could put to the 1, but you don't have to, times 0.2. There you go. We get an answer of 0.15. All right, when you press enter, the format should be the same as the format here. All right, so the next problem is going to have more in the denominator, and I'll work through that with you. Okay, so in a shoe store, the probability that a person buys 0, 1, or 2 or more pairs of shoes are 0.3, 0.6, and 0.1 respectively. So our categories are how many pairs of shoes you buy. So we could have 0 pairs, right? 1 pair, or 2 or more pairs. Their probabilities are 0.3, 0.6, and 0.1. Remember, when it says respectively, that means this order matches the order in which it was listed earlier in the problem. We have, if 6 customers enter the store, find the probability that 1 won't buy any shoes, 3 will buy 1 pair of shoes, and 2 will buy 2 or more pairs. So we're going to have 1 buys none, we're going to have 3 buys 1 pair, and 2 people buy 2 or more. Double check your X's add up to the sample size of 6 customers. So now let's plug it in. Okay, in our probability formula, it goes n factorial over x factorial, x factorial, x factorial. And then we're going to have 0.3 raised to its x1 times 0.6 raised to the third times 0.1 raised to the 2. All right, let's try typing it in. We're going to make a fraction. We're going to have, oops, sorry, I'm off the screen. We're going to have 6 factorial over, go down to the bottom, 3 factorial, 2 factorial. You can type in 1 factorial, but it's multiplying by 1, it doesn't make any difference. Okay, then I'm going to have times 0.3 to the 1 power times 0.6 to the 3 power times 0.1 to the 2nd power, or squared. All right, so you should have that. And when you press enter, there's our answer, 0.03888. Again, like always, write down whatever notes you need. So if you have calculator things that you want to jot down, go ahead, jot them down. If you have little tricks about this formula, jot them down. Star, don't forget, blah, 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 whatever you want. So pause the video right now and try number 3 on your own. Okay, and then I'm going to explain it, but try it on your own to get started. So if you unpause now, a box contains 4 white marbles, 3 red marbles, and 3 blue marbles. So our categories are white, red, and blue. All right. A marble is selected at random and its color is written down. It's replaced each time. That way our probabilities are consistent. We want to find the probability that if 5 marbles are selected, 2 are white, 2 are red, 1 is blue. Well, this is a little different because I didn't give you a percentage, right? I didn't give you 50%, 30%, or 0.6 or something like that. But how can we come up with our probabilities? The probability of picking a white marble comes up here. There are 4 white marbles out of a total of 10. So it's 4 out of 10. I'm just going to write 0.4 because it's easier to put in the calculator, which means my probability for red marbles is 3 out of 10, and the probability of picking a blue marble is 3 out of 10. Okay, these numbers down here give me my x's. Because my n is 5, if 5 are selected, whatever is selected is your sample size. So if my n is 5, I know that my x's need to add up to 5. I want the probability that 2 are white, 2 are red, and 1 is blue. Now, if you had gotten stuck on setting this up, now pause it again, and now that we have the table set up, do the formula and do the answer. Okay, so pause, do the formula, do the answer, then come back to me. All right, we're going to have the probability is going to be 5 factorial over 2 factorial, 2 factorial, 1 factorial, 0.4 squared, 0.3 squared, 0.3 to the 1. When you put that all in your calculator, you should be getting an answer of 0.1296. Okay? If you don't know what I just did, or if you're having trouble, I need you to let me know so that I can help. You know I would love to help. All right, so multinomial. recap is when you have more than 2 categories. This one should stand out all on its own because it's really the only time we're going to have lots of categories in this chapter. Okay. The other distribution we're going to talk about today is the Poisson distribution. Okay. It's going to look like poison, but it's really called the Poisson distribution. All right. And when we have the Poisson distribution, there's a couple big things that we need to talk about. All right. The first is when you have a large sample size. This is going to, and you probably want to make a note to yourself, this is going to seem very similar to the binomial distribution. Okay, you're going to have like success and failure again, but the big change is that you can either have a large sample size, all right, like we're talking n is 100, 2,000, all right, 500, 250, something big. Okay, you're going to have a big sample size. If you look back at section 6.3, every single binomial problem, the sample size, I would imagine, was 25 or less. All right, always small sample sizes. I'm not going to give you anything gray in the middle. It's either going to be big or it's going to be small, like 25 or less, maybe 30 or less. But I won't give you like a 32. All right, it's going to be big like this or small. All right, and the other thing that we need to talk about is that this problem uses averages. Okay, and the symbol for average is this upside down Y. It's called lambda. It's a Greek letter, and it represents your average, okay, which I put here. Lambda is your mean number of occurrences. Here's your formula, but I'm going to be really honest. I'm just going to go straight to the calculator shortcut. Multinomial, there are no calculator shortcuts. They don't exist. If you find one, please share with the rest of the class, but I haven't found one. This guy has a calculator shortcut in the same spot that we had the binomial. So I'm actually going to go straight to the calculator to work through this. All right. Now, your averages, your lambda, can be found a couple different ways. Sometimes you need to use lambda equals n times p, which is the formula to find the average binomial as well. Okay. Sometimes you need to figure out your lambda like we're going to do in number 4. Sometimes the lambda is just given to you, and I'll give you another example of that. All right. So with this, you really, for the calculator, only need lambda and x. That's it. Those are the only things you need. Okay. So example 4. If there are 200 typos randomly distributed throughout a 500-page manuscript, we want to find the probability that if we open any page, that it contains exactly 3 errors. So, going back to the fact that all we need is a lambda and an x, all right, then this exactly 3 should be the same thing that exactly 3's been for the past couple lessons. This is going to be our x equals 3. All right, it's how many we want. Our average this time we're going to use here. If you have 200 typos spread out throughout 500 pages, then we have this concept of 200 typos out of 500 pages. If you do 200 divided by 500, you're going to get an average of 0.4 errors or typos per page, right? And let's think about this. If you have an average of 0.4 errors per page, and we're looking for 3 errors on one page, that's going to be really unlikely, right? If you have less than half of an error per page, and we want to find the probability that there's 3 errors on a page, that's going to be a pretty unlikely scenario, okay? Poisson has PDF and it has CDF, the same criteria that it had before. PDF is exactly 1 x, and CDF is a cumulative range of x's. So we have x equals 3. So we're going to be using PDF for this problem. All right, so in our calculators, we're going to go back to menu, probability, distributions. All right, and it's right here at the bottom. Notice I was up top. If you hit the up key, it wraps to the bottom. Pretty neat. So I'm going to pick Poisson PDF. It asks me for my lambda is 0.4. It asks me for my x value of exactly 3. And I'm going to just press enter, and I'm going to let it do the formula for me. Okay. Just like we did with the binomial distribution, you need to write down it's Poisson PDF, and then it's lambda comma x equals 0.0072. This is our answer. Again, this was lambda comma x. That's how it went. Alrighty. So, next problem. Ooh, I called them both example 4. My bad, this should be a 5. Sorry. So, this guy, it's saying if approximately 2% of the people are lefties and there are 200 people in a room, okay, we want to find the probability that if we pick people, what's probably that exactly 5 of them are going to be lefties. All right, so exactly 5 is going to be x equals 5. But we need to find our average. On average, how many lefties would we expect out of 200? If there are 2% of people are lefties and there's 200, this is your n and this is the p. So this is the type of problem where you would use n times p to figure out lambda. Back here we had to logically figure out our average by dividing them down. Okay, this time we can logically figure out, well, what's 2% of 200, right? 200 times 0.02 would give us an average of 4 lefties. So we want to know the probability of getting 5 lefties. It's not bad. That's pretty close, right? So once you find your lambda and your x, you can go to your calculator. You're going to do the same thing I just modeled. Poisson PDF, and it goes lambda comma x. So our lambda is 4, our x is 5. Okay, because remember lambda represents average. And when you guys do that in your calculator, you should be getting 0.1563 as your answer. All right, so last problem for today, number 6. A sales firm receives, on the average, 3 calls per hour on its toll-free number. So for any given hour, we want to find the probability that it's going to receive these sets of calls. Now, some of you might be like, oh, we don't have enough numbers. Right? That's typically a lot of reactions, but we do. It tells us that they receive an average of 3. So it already gave us lambda equals 3. All right. This time it just handed it right to us. So we already have lambda equals 3. If it says at most 3 calls, this is our x. So x, if it's at most 3, it includes 3. So it starts at 0 and goes up to 3. All right, because at most can include 3. So this is a cumulative range. So you would go back in your calculator, you would pick Poisson CDF this time. Okay, here we go. Menu, probability, distributions, way bottom right there, Poisson CDF. Okay, lambda is 3. The lower bound is 0. The upper bound is this 3. And we get an answer of 0.6472. All right, lambda, lower bound, upper bound. All right, so at least 3 calls means x can start at 3 and go up to, well, this one's different. It doesn't give us an end. We don't have a fixed number of trials. So technically, it can go to infinity. All right, now, if we can go all the way up to infinity, when we type this in our calculator, when we have Poisson CDF, it goes lambda, lower bound, upper bound. Your lambda is 3, your lower bound is 3. Your upper bound, you can't type in the infinity symbol. Like, yes, you can find it, but the calculator doesn't recognize the infinity symbol as actually being the number infinity. So to get around that, hang on, let me change this. I just type in, a really big number, okay? I just go like 55555. Just pick a really big number compared to the other numbers that you had here, okay? So I just go like 5555 or 66666. Just hit the same number a bunch of times. Just make sure it's a big number, and that will act like infinity for our purposes. The differences between, if you pick like such a huge number, it might be like out in this last decimal place, it might be a 4. Okay, but for our purposes, you can't hit the infinity button. You can handwrite the infinity symbol, but you're going to have 0.5768 as your answer. So, last but not least, 5 or more calls is going to be x equals 5 to infinity, because again, it's open-ended for this. So you'd have Poisson CDF. Lambda is 3, lower bound 5, upper bound infinity. Go ahead, type in a huge number, go pick one, and I bet we're going to have the same answers of 0.1847. All right, let me know whatever questions you have, and yes, of course, as always, we're going to practice. Bye.